This is the final exam for MBA211, page 4, part 2. Programming testing, unit testing, page 513. Programming. During the programming, this is on the exam stage, system specifications that were prepared during the design stage are translated into software program code. Today, many organizations no longer do their own programming for new systems. Instead, they purchase the software that meets the requirements for a new system from external sources, such as the software packages from a commercial software vendor, software services from an application service provider, or outsourcing firms that develop custom application software for their clients. See section 13.3. Second point here on the exam is testing. Testing. Exhaustive and thorough testing, this is on the exam, must be conducted to ascertain whether the system produces the right results. Testing answers the question, will the system produce the desired results under known conditions? As Chapter 5 noted, some companies are starting to use cloud computing services for this work. The amount of time needed to answer this question has been traditionally underrated in systems project planning. See Chapter 14. Testing is time-consuming. Test data must be carefully prepared, results reviewed, and corrections made in the system. In some instances, part of the system may have to be redesigned. The systems resulting from glossing over this step are enormous. Testing an information system can be broken down into three types of activities. This is on the exam. Unit testing, this is on the exam. System testing, and this is on the exam. Acceptance testing, this is also on the exam. So unit testing, this is on the exam. On program testing consists of testing each program separately in the system. So unit testing is also called program testing and consists of testing each program separately in the system. It is widely believed that the purpose of such testing is to guarantee the program are error-free, but this goal is realistically impossible. Testing should be viewed instead as a means of locating errors in programs, focusing on finding all the ways to make programs fail. Once they are pinpointed, problems can be corrected. So the following on page 4, systems testing, acceptance testing, test plan, conversion, parallel strategy, direct cut over strategy, page 514, are all in the exam. So the first system testing, the first point here is on the exam. System testing tests the functionality of the IS as a whole. It tries to determine whether discrete models will function together as planned, and whether discrepancies exist between the way the system actually works and the way it was conceived. Among the areas examined are performance, time, capacity for file storage and handling peak loads, recovery and restart capabilities, lastly, manual procedures. So that was system testing, and that is on the exam. Acceptance testing, also on the exam, provides the final certification that the system is ready to be used in production setting. Systems tests are evaluated by users and reviewed by management. When all parties are satisfied that the new system meets their standards, the system is formally accepted for installation. So this is on the exam, acceptance testing. The next point here, point number 3, the system development team works with users to devise a systematic test plan. The test plan, which is on the exam, includes all of the preparations for the series of tests we have just described. Figure 13.5 shows an example of a test plan. The general condition being tested is a record change. The documentation consists of a series of test plans, screens maintained on a database, perhaps a PC database that is really suited to this kind of application. The next point here, point number 5, is conversion, is a process of changing from the old system to the new system. 4 main conversion strategies can be employed: the parallel strategy, the direct cutover strategy, the pilot study strategy, and the phase approach strategy. In a parallel strategy, both the old system and its potential replacement are run together for a time until everyone is assured that the new one functions correctly. So that's the parallel strategy, which is on the exam, and also conversion. This is the safest conversion approach because in the event of errors or processing disruptions, the old system can be used in the backup. However, this approach is very expensive, and additional staff or resource may be required to run the extra system. So that is parallel strategy. Figure 13.5, a sample test plan to record a change. So this is the end of page 4. When developing a test plan, it's imperative to include various conditions to be tested, requirements for each conditions tested, and expected results. Test plans require input from both end users and information specialists. So page 5. The last point here is that's on the exam is the direct cutover strategy. This replaces the old system entirely with the new system on an appointed day. It is a very risky approach that can be potentially be more costly than running two systems in parallel if serious problems. Let's go back. If serious problems with the new system are found, there is no other system to fall back on. Dislocations, disruptions, and cost of corrections may be enormous. Okay, so the next line item on page 5 is pilot study strategy, phase approach strategy, documentation, production, post-implementation, audit, and maintenance, all on page 515, are on the exam. The pilot study strategy introduces the new system to only a limited area of the organization, such as a single department or operating unit. When this pilot version is complete and working smoothly, it is installed throughout the rest of the organization, either simultaneously or in stages. The second part of the exam will be on phased approach strategy. It introduces the new system in stages, either by functions or by organizational units. If, for example, the system is introduced by function, a new payroll system might begin with hourly workers who are paid weekly, followed 6 months later by adding salary employees who are paid monthly to the system. The system is introduced by organizational unit. Corporate headquarters might be converted first, followed by outlining operating units 4 months later. Moving from an old system to a new one requires the end users to be trained to the new systems. Detailed documentation showing how the system works from both a technical and end user standpoint is finalized during conversion time for in training and everyday operations. So detailed documentation, which is on the exam, showing how the system works from both technical and end user standpoint, is finalized during conversion time for use in training and everyday operations. Lack of proper training and documentation contributes to system failure, so this portion of the systems development process is very important. So uh, data flow diagram, which is on the exam, is the primary tool for representing a system's component process and the flow of data between the DFD, which is the data flow diagram. The data flow diagram offers a logical graphical model of information flow, partitioning a system into modules that show manageable levels of detail. It rigorously specifies the process or transformations that occur within each model, interface that exists between them. So here is a model of student request courses. So this is figure 3.6. The diagrams can be used to depict higher level processes as well as lower level details through level data flow diagrams. A complex process can be broken down to successive levels of detail. An entire system can be divided into subsystems with a high-level data flow diagram. Each subsystem in turn can be divided into additional subsystems with second-level data flow diagrams, and the lower-level subsystems can be broken down until the lowest level of detail has been reached. Process specification structure chart, page 517, is on the exam. Another tool for structure analysis is a data dictionary, which contains information about individual pieces of data and data grouping within a system. Chapter 6, the data dictionary defines contents of data flows and data stores so that systems builders understand exactly what piece of data they contain. So process specifications, this is on the exam, describes the transformation occurring within the lowest level of the data flow diagrams. They express the logic for each process. In structured methodology, software design is modeled using hierarchy structured charts. Structured charts, this is on the exam, is a top-down chart showing each level design, its relationship to other levels, and its place in the overall design structure. The design first considers the main function of a program or system, then breaks this function into subfunctions and decomposes each subfunctions until the lowest level of detail has been reached. Figure 13.7 shows a high-level structured chart for a payroll system. A design has too many levels to fit onto one structured chart. It can be broken down further on more detailed structured charts. A structured chart may document one program, one system, instead of programs or part of one program. That's the end of page 5, and we'll go to page 6 here, and we'll describe systems lifecycle, which is on the exam, page 520. The systems lifecycle, which is on the exam, is the oldest methods for building IS. The lifecycle methodology is a phased approach to building a system, dividing system developments into formal stages as illustrated on figure 13.9. System development specialists have different opinions on how to partition the systems building stage, but they roughly correspond to the stages of system development we just have described. The systems lifecycle methodology maintains a formal division of labor between end users and information specialists, technical specialists such as systems analysts, programmers are responsible for much of the systems analysis, design, implementation work. End users are limited to providing information requirements and reviewing technical staff's work. The life cycle also emphasizes formal specifications and paperwork, so many documents are generated during the course of the systems project. So here, figure 13.9, which might be on the exam, is systems analysis, systems design, programming, testing, conversion, production, and maintenance. So those are each stage of the systems lifecycle. Systems lifecycle is still used for building large complex systems that require rigorous and formal requirements analysis, predefined specifications, tech controls over the system's building process. However, the systems lifecycle approach can be costly, time-consuming, and inflexible. Although system builders can go back and forth among stages in the lifecycle, the systems lifecycle is predominantly a waterfall approach in which tasks in one stage are completed before work for the next stage begins. Activities can be repeated, but the volumes of new documents can be generated and steps retrace if requirements and specifications need to be revised. This encourages freezing or specifications relatively early in the development process. The lifecycle approach is not suitable for many small desktop systems, which tend to be less structured and more individualized. Okay. So prototyping and prototype, page 521, which is on the exam. Prototyping consists of building experimental systems rapidly and inexpensively for end users to evaluate. By interacting with the prototype, users can get a better idea of the information requirements. The prototype endorsed by users can be used as a template to create the final system. The prototype, which is on the exam, is a working version of an information system or part of the system, which is meant to be only a preliminary model. Once operation, the prototype will further refined until it conforms precisely to user requirements. Once the design has been finalized, the prototype can be converted to a polished production system. The process of building a preliminary design, trying it out, refining, and trying it again has been called the iterative process, which is on the exam. Iterative process of systems development, because the steps required to build a system can be repeated over and over again. So iteration is repeated over and over again. Prototyping is more explicitly iterative than the conventional life cycle. So prototyping is more explicitly iterative, repeated than a conventional life cycle. So those are separate things. It actively promotes system design changes, and has been said that prototyping replaces unplanned rework with planned iteration, with each version more accurately reflecting user requirements. So iterative process and prototyping process, page 522 is on the exam. Steps in prototyping. Figure 1310 shows a 4-step model of the prototyping process, which consists of the following. Step 1. Identify the user's basic requirements. The systems designer, usually an IS specialist, works with the user only long enough to capture the user's basic information needs. Step 2. Develop an initial prototype. The systems designer creates a working prototype quickly using tools for rapidly generating software. Step 3. Use the prototype. The user is encouraged to work with the system to determine how well the prototype meets his or her needs and to make suggestions for improving the prototype. Step 4. Revise and enhance the prototype. The system builder notes all changes the user requests and refines the prototype accordingly. After the prototype has been revised, the cycle returns to step 3, which is use the prototype, and step 4 are repeated until the user is satisfied. Revise and enhance the prototype. So figure 1310 shows you the steps. Step 1, basic requirements. Step 2, develop a working prototype. Step 3, use the prototype. And between step 3 and 4, there is a decision triangle or diamond that says user satisfied. If yes, operational prototype. If no, revise and enhance the prototype, and you repeat step 3. The process of developing a prototype can be broken down to 4 steps. Because a prototype can be developed quickly and inexpensively, system builders go through several iterations, repeating 3 and 4, and refine and enhance the prototype before arriving at the final operation 1. Okay, so I'm going to stop here, the prototyping process. This is page 7. Almost done here. Got one more paragraph, but the video is going to end. Prototyping process. One more bullet point.